physical description of it, and then we're going to go through some of the experiments quite quickly. I don't have time to get into details. My talk tomorrow, by the way, gets into more detail of one of my favorite experiments. And then things that we just didn't think about, problems that arose using this lab-based course. So we call that fine-tuning the course, putting out fires. I'm in a statistics department. There's 10 of us, and we value good teaching. And one of the things that we do is meet during the lunch hour on a fairly regular basis and have what we call the Do It seminar. That's an acronym for Discussions on Improving Teaching. And we sit around and share with each other what we are doing, not doing, what's good, what's bad. And one of the topics that came up several years ago, because this lab-based approach has been in use for about 6 years, is that our Stat 201, that's the number of the Intro Stat course, was not a very good course. We didn't feel that we were really giving the students a very good product. Also, about the same time, National Science Foundation and some other major grant agencies were making monies available for things just along these lines, for buying equipment to set up a lab, or for changing the curriculum in a certain course. And so there was monies out there. Even at a local level, we had money available from our president's office. One of the things that my co-author John Spurrier mentions as a motivation is something he calls value of memorable experiences. If you talk to a person that has had a stat course or even a math-based course, one of the things that they'll mention is if they had any real-life experiments, or if they did any counting M&Ms or pillars of M&Ms, they remember that more than this eloquent proof that we showed them of the central limit theorem. And so, and a few other people argue this. Bill Parr, a person who teaches industrial short courses at the University of Tennessee, is a big proponent of the value of memorable experiences, and his course has 3 or 4 breakout sessions a day where the students who are industrial workers do experiments. My coworker John Spurrier has little kids, and he would see them each week watching TV and seeing shows like Mr. Wizard, which is a local show where this TV weatherman actually does little experiments on TV, and then the Square One TV programs. And the kids were learning, his little teeny-weeny kids were learning statistical concepts through these experiments better than our college freshmen. Another story that John tells is that in a physics lab he had during college, it produced messy data. It was a typical science lab in which the data were supposed to verify some theory, and his data were messy. And his lab partner, who had the same data because they worked in teams, fudged it, killed off some outliers, and he got an A on his physics lab report, but John Spurrier made a B because he used the real data. And he felt that was a very scary message that maybe some scientists were teaching students to throw out data. We all know that's a no-no. Our computer component in Stat 201 was a few assignments in which the students were sent to some place that had Minitab across campus and pretty much set free to do these assignments. There was one on descriptive statistics where they generated some pretty pictures. Data sets were in the textbooks. So it was pretty standard. The course was 3 hours of lecture per week, and homework was done by hand and a few of these computer assignments. Well, the students just didn't like the computer component. They saw it as a time waster. I mean, the actual walking 15 minutes across campus bugged them. And we were not successfully showing them that the computer can be useful. Another negative of the Stat 201 before it changed is we didn't give the students a lot of practice with written communication. Now, these labs that they do weekly, they are assigned one what we call extended writing assignment, and they do have to write a report. So that's an added component that wasn't in the course before. They're allowed a rewrite also because they start off a little bit rough. We find that students had a bad impression of what statisticians do. Like we decide whether or not to reject the null hypothesis, that's our life. And they just didn't think that it was a very appealing career. No wonder they did not, say, take more courses or go into statistics as a major. We started off with some monies from the local level. The provost had a grant competition, and I think we won like $5,000 to buy a high-end PC, which is what it cost back then, and equip it with Minitab and make it sort of the prototype of what might be in a computer with more of these machines. That looked good on our applications for grants to the National Science Foundation. Then we'd gotten some seed monies from the local level, and then we were able to get some more bigger monies to equip these grants from the National Science Foundation. And this is all in the past. We're not currently funded because the course now is deemed a lab course, like a chemistry intro course or a biology course. And at University of South Carolina, when something has the lab course distinction, the students, in addition to paying the tuition for the 3 hours of statistics, pay a $25 lab fee. And it comes straight back to our department. This generates about $17,000 a year. And that's more than we need to replace the computers every now and then. But I feel a little guilty that they pay that big of a lab fee. But that's what it is. And it was a major coup on the part of our new dean, because he made that a stipulation of coming to the university, that we charge a lab fee for lab courses. Okay, let me point out, as I'm talking about these course goals, some facts about what I have at USC. The course typically has an enrollment of about 325 students a semester. And we refuse to go to a large section environment where they all meet in one room. And so we have about 8 sections of 46 students each. Seems large to me, but that's as big as we get, 46 in a class. On 2 of the 3 meeting times per week, they meet in the lecture room, a traditional lecture room where the teacher, not always me by the way, teaches them some new ideas and goes to the board and writes examples. Maybe has wheeled in a computer to show them some examples. The 3rd meeting, however, is the lab. It's usually the end of the week, and they go to an entirely different room. The class of 46 is divided up into 2 groups of 23 each, and so the labs rooms have 12 computers and handle 24 or 23 students. So that's the numbers we're talking about. Another big issue, another big thing we had to keep in mind is at University of South Carolina, this intro stat course, typically there are 9 sections, and only one of them is taught by a tenured faculty member. Every other one is taught by a PhD graduate student. That's just the fact of life at a major state university. And so we had to use an approach that they would buy into and that they would excel at and do well. The goals of the course were, of course, to have the students learn ideas through doing instead of just having us talk at them. In our lab manual, I'm not trying to sell any books today, but this is the lab manual the students have to buy to do the 17 experiments. On the page that has all the dedications to wives and parents and dogs, we have an ancient Chinese proverb. What I hear, I forget. What I see, I remember. What I do, I understand. And we like that because we see that in action over and over. And so these were our goals. I've already mentioned most of them. And let's see how we did this. Okay, so each week, usually it's the 3rd meeting of the week. That is Monday and Wednesday, they have come to the lecture format, and on Friday they go to the lab room. They meet, and working in teams of either size 2, 4, or those are the team size, or sometimes alone, discuss an experiment. And the experiments are all, well documented in this book. The most the teacher has to do, the TA, is to have pre-read the experiment, the lab section, and hopefully have done the experiment. But they can sometimes don't even have done that. And the students just decide on certain issues that they're dependent on what experiment I'm talking about. I'll get into more detail on that later. And then start carrying out the experiment. A lab session, by the way, is 2 hours. And every lab fits in 2 hours, no problem. Sometimes we get done even a lot earlier. I spent so much time designing this little fancy lab setup that I put too many students in the room. There's only 24 students. So at each of these 6 tables, there's 4 students sitting. Yeah, if you look real closely, we've got Wilma, Fred, an M&M. So that'll show you not to waste time making pretty pictures. The computers in our lab are around the edge of the room. 12 computers, because a lot of half of the time is spent doing the measurements of the hickory nuts or going outside and flying the balsa wood airplane. And then the data analysis are done during hour number 2. So this is a little bit different than what you've been hearing about so far, in that we have as many as 24 different data sets in a typical experiment. I cannot underestimate the value of the students having their own data. You would just see so much excitement when it's their own data, when it's their own guessed distances from going outside and hitting golf balls, or it's their own plane flight lengths, rather than if we hand them data or provide them with real data. I don't mean to knock that approach, but I'm continually impressed by how excited they get that they have their own data set. We start off with a session that introduces students to the computer and to the Minitabs computer package. 6 years ago when we started this, many students didn't even know how to drive a mouse, and so we had to get them used to that. And now they just fly through that section of the desktop and all these issues about a computer. But half of the chapter in Chapter 1 is devoted to students learning the computer, and then the second half, Phase 2, a little bit about Minitab. Okay? So there's no lecturing at them about these issues. They learn it all through the lab. The book has computer screens that if they can see, they can get through this without any help from us. What happens, of course, is they try to shortcut and get lost or too far ahead. What the teacher, me, or in the case of a TA, does is just sort of flit around the room, and motivate the students to think about their data, or sometimes put out fires if they've messed up by doing something wrong. These coincide with what's being taught in the lecture. So if you think about it, what do you first teach? You're teaching them descriptive, both numerical and graphical techniques during those first couple weeks. And so the real-life data set that we use to show these ideas are heart rates. So students take their own heartbeats in lab number 2. And we do a minute rate, but it's based on a 15-second count that's multiplied by 4. And they get 8 of those. And then we make them do it again, this time counting for 30 seconds and multiplying by 2. And we get 8 of those. And it's a real clear example of variability, because the variability of the second one is smaller than the variability of the heartbeats based on taking 15 seconds and multiplying by 4. You ask them what a nurse does, a nurse just does it for 10 seconds. But it's kind of a boring but effective lab. It doesn't have many materials, only a stopwatch, or the computers now can serve as that, and a heartbeat. Some of our students actually do not have heartbeats. They can't find it, and we don't make them. It's amazing to me. Okay, I'm going to go quickly now because I don't want to spend too much time. On my handout, it's not in this step, it describes every one of the 17 labs and what, just a second, I'm just going to do that, and what statistical concepts it covers. Author is basically a discriminant analysis lab. The 17 chapters of this book are written by 3 different authors. I wrote 5 of them, John Spurrier wrote 6 of them, and Don Edwards wrote 6 of them. And so what we do is we use the first page of not this page, but the first page or 2 as a sample page from that author's writings, and we provide them with a disputed manuscript. It's a lab session that used to be in the book, but it is no longer because it costs us too much. And they're asked to use this textbook along with who wrote each of the 17 chapters and decide who wrote, because it's one of us 3, the disputed manuscript. And it's kind of a neat example of discriminant analysis. They don't know they're doing that, but they basically, the students working in teams define variables like the number of these on the page, or the number of occurrences of a comma on the page, or the average length of a sentence on the page, or even the average, the number of words on a page. And they can pretty much figure out that the disputed manuscript was written by Dr. Toombs, using only graphical statistics. Another one that has a before and after feature to it is plant growth experiment. The students, again, don't know it, but they're carrying out a 2 by 2 factorial experiment in which 2 varieties of a certain plant, like corn, and 2 different watering schemes are being compared to see what grows the biggest and tallest. So this is carried on for 8 weeks, and it's analyzed later on. This is the one, this next one I'll talk about tomorrow. I love this lab. We take the students outside, we tromp all 24 of them outside, and we stand at a reference point. It's all determined. This is sort of the background work that we have to do to make everything go smoothly. And they stand all around a reference point and guess distances. Okay, landmark number 1 is the distance to that back camera. How many feet do you think it is? And they write down their guess. We do this 12 times. The true distances are also measured by the students working in teams, so they get a feel for variation in measurements, because every distance is measured by more than one team, and by golly, they don't all have the same measurement. They can be off by sometimes as many as 50 feet if it's a measurement that used the tape measure 3 or 4 times. So, you know, it illustrates the usefulness of the median, because we have 3 teams measure each landmark. It's a great lab. And then they do a regression analysis complete with the calibration experiment, in which their guesses can be calibrated to be pretty darn close to the true, because there's this mystery landmark in which they've guessed the distance, but we don't tell them the true. And using the regression line, they calibrate their guess, and it's just uncanny how well it calibrates to the true distance. Our time series lab, another optional one, because this is not covered in class, is a lab in which the students count cars at various intersections. And we see some nice cycles depending on the traffic light at the corner. Another favorite, lab number 5, as we call it, the taste test. The students working in teams carry out a taste test. And it's a taste test in which the other students are the subjects, and they're asked to choose their favorite. The concepts it illustrates are binomial p-values, because if the 2 products that you're giving them are equally preferable, then the probability that people chose, the name brand product over the other one should be a half. And so we compare things like cheap cola versus Coca-Cola. You know, everybody's grocery store has a generic brand. This is one where over and over again, the generic brand cola will get chosen over the more expensive Coca-Cola brand. And they're just, you know, so disgusted with themselves that as a whole, they chose Bilo brand cola over the name brand. And in the meantime, they're learning how to carry out a hypothesis test or interpret a p-value. Let's see. Recently, we jumped on the fat-free bandwagon and compared fat-free cookies to non-fat-free cookies. And nobody likes fat-free cookies. They taste like, what have we heard? Cardboard, particle board. They don't like them. So those never get chosen. We don't always do food Sometimes we do things that smell, based on smell and touch. We let the students leave the room for this one. They take tissues and just hold it to their face, and overwhelmingly prefer the more soft tissue, which doesn't surprise you. And so that's another one of our favorite ones. Measuring carpet tacks using micrometer illustrates variability among other things. A simulation experiment, you know what those do, illustrates the central limit theorem, and also we simulate the sampling distribution of the median. We're big on the median. This one is known as the airplane lab, the Balsam Wood Airplane Lab. Each student, each team is provided an airplane. And we're real cheap at University of South Carolina, so we use these airplanes over and over again. And basically, they're provided a pile of airplane parts, like a body, a wing, a tail, and a tail fin, or whatever it's called. We don't even use pilots anymore. And they assemble an airplane and then define two new factors. Like some of them want to see if the airplane would fly farther if they add a paper clip to some part of the plane. That's a common choice. Others want to investigate the effect of the shape of the wings. They'll add a different shaped wing. Moving it forward and backward in the slots is kind of a boring choice, but a common choice of factors. Some take the wings and turn them upside down because they do have a slight angle. And so they define two factors, each at two levels, and go out and fly the airplane 16 different times, so replication 4, and see which factor level combination did best. And in our definition, best is defined as farthest, not straightest, but simply farthest. In the meantime, they're learning issues about randomization because they don't go outside and fly all 4 flights, say with the wings forward and the paper clip on, all at once. They've predetermined using random number simulation a random ordering of the 16 flights. And you know, they're outside and a big gust of wind comes up and they see why randomization is important. The airplane lab is a continual favorite. Breaking strength, we use tissues and spread them on an embroidery hoop. It's really funny to see people doing that, especially guys. And then drop very lightly fishing weights. Okay, not drop, place fishing weights on the tissue to see how many it holds before it breaks. Okay? And one year we used the university supplied tissue and we ran out of fishing weights. It was so rough and tough that each group was getting to like 32 little teeny fishing weights and it still wouldn't break. So we go all out and buy name brand soft tissue for this experiment and get measurements like 7, 10, sometimes they'll get 16. But when the fishing weights break through the suspended embroidery hoop, a big loud noise occurs, and you know, they just love it. They have so much fun, and then they wheel themselves over to the computers and do a 1 sample t-test or a 1 sample confidence interval. The analysis of the plant data comes about in week 13, and admittedly we don't do that one for the masses. I teach the honors section of this class, and I sometimes will do it. The race to solution is our in-house analogy to the airplane experiment. The students measure the dissolving times of 2 brands of aspirin when they're dissolving in vinegar versus water. Vinegar is supposed to simulate an upset stomach, I guess, and water a more normal condition. And the dissolving times are real different. Now we're into the part of the semester in which the students know things like paired t-test. They're learning 2 sample inference. And so these last 4 or 5 experiments are more involved. They have they take up the whole 2 hours. They have more materials, and I think that it sort of like culminates in these last few. Here's what Walk This Way is. Students go outside, and we have them walk using 2 different arm styles. One is the exaggerated style. You almost walk like a tin man, and the other is the arms and hands style, and you keep your arms and hands, your arms at side style, and we measure heartbeat before and heartbeat after. So again, the student has to have a heartbeat. So heartbeat before, they walk according to the style that the coin flip determined. Heartbeat after. We also measure how long it took them to walk that circle. So lots of measurements. Everybody has about 8 different numbers. And we go inside and do all sorts of paired t-tests. Increase in heartbeat for exaggerated style versus increase in heartbeat for the arms at side style to sample. That actually collapses to a 1-sample t-test. And the data is a whole class data set, so that is a lab in which everybody's working with the same data. You don't have 6 different data sets. Absorbency of paper towels, the Bounty Quicker Picker Upper. We compare the absorbency of 2 brands of paper towels. They actually dip the paper towel using tongs in a bucket of water, hold it and let it drip for 20 seconds, and then measure it using one of the electronic scales. I'll get into the materials of all these labs. They're not that expensive. The most expensive is the digital electronic scale. It measures in grams, or it'll measure in anything you want to measure. It's also the most commonly stolen. Wonder why? Hickory Nut Lab, the students are now seeing their 2nd visit of regression in class because we use a book written by some, it's called Just the Essentials. It's written by some professor at a community college in New York. It's what I've been saying for 8 years, now I know, Dr. Robert Johnson. And so we come back to regression and do a little bit more inferential stuff. We show them that you can predict the weight of a hickory nut based on some external measurements pretty darn accurately.
What is the hickory nut?
A hickory nut comes off the tree. It'll make the blade of your lawnmower actually break.
What do you do with hickory nuts in this lab? I wasn't sure.
We measure the weight in grams. That's the Y variable. And we measure how tall it is. There are actually a top and a bottom. And then we have something called a major axis and a minor axis. And that has the students turning the hickory nut until it looks the skinniest, and that's the minor axis. And then they're turning the hickory nut until it looks the fattest, and they measure that width, and that's the major axis. They get pretty good at these. And so those 3 measurements, height, major, minor, are used to predict the weight. It's another good illustration of proxy measurements because the best predictor is the single predictor defined as the product of those 3 measurements. And the product of those type of measurements is just a proxy for the volume of the nut, and so no wonder it is the best predictor of the hickory nut. And the hickory nuts are irregularly shaped, and so we get issues about outliers come up and stuff like that. We call the little nodules that form on these hickory nuts nipples. So you have a class of freshmen talking about measuring the weight of their nuts, some with nipples, all with a straight face. It's pretty amazing. One of our more boring labs, I'll attest to that, is selecting a random sample. And issues like the sampling frame, random number generators are illustrated. The students go to a parking lot and select a sample of cars. We include this in the book because it serves as a perfect makeup lab. Because once you add this component to a class, it's not uncommon that students will miss a lab, and so we have the fix for that problem being the makeup lab. Okay, materials. A lab that handles a weekly crowd of 24 students can be equipped, computers and all. We said $2,000 one time. Now, how do you get that one? That wouldn't cover the computers. I think the $2,000 was based on just these materials. That's gone down, I bet. But if you figure 4 per group, then you need as many as 6 groups, and so 6 sets of these equipment. The scale, I said that's more expensive. It's a nice digital scale that measures the weight of a hickory nut. It also serves to measure how much water the paper towels absorb. So it's used several times. The caliper is for measuring the hickory nuts, among other things. Measuring tapes we use over and over again. I have sort of an ongoing battle with my co-authors. I want to go ahead and buy these $40 measuring tapes that have a lifetime guarantee. And so when they break, because the students have stepped on them outside while measuring distances, we can get a free replacement one, I think. But now we still buy the cheapies that break about every other semester. They break, and that's our most breakable object. The micrometer is a nice metal micrometer that will measure real small measurements like these carpet tacks. And that's a kind of an expensive item too. Stopwatches, we go through those a lot, but students nowadays have watches and sometimes don't even use a stopwatch. Other less expensive things, rulers, airplane, paper towels, got some scissors that those come in handy when you're cutting wings in the plane. Some food items for the taste test lab, some buckets, bowls, and tongs. We find that each semester for the 325 students, some of these items that you have to buy each semester, like the food, are less than $50. That's no lie. This isn't very expensive to equip. Each week, the students either do a short writing assignment, it's as part of the in part of the lab manual, and they tear it out, which is 6 or 7 essay-type questions, or a longer assignment. Oops. The so-called EWA, an acronym for Extended Writing Assignment. So this becomes part of our vocabulary. Okay, is this an EWA week or a SAWA week? This is a SAWA week, and your SAWAs are due Monday. SAWA, they do all but 2 weeks, because I make them write extended writing assignments 2 weeks. This is a little bit different for the teaching assistants that teach the courses. They only can handle 1 writing assignment and only assign 1. And we have favorite labs that we assign these formal papers to. The airplane lab's an excellent one. I like the distance guessing lab, the taste test lab. You want to choose a lab that is one of the more interesting labs. There's a appendix in the lab book that Dr. Who wrote it? Edwards wrote. And I love it. It's a technical writing report appendix. It shows examples of bad writing and good writing. Because the EWA is quite an assignment. It counts as a whole test for them. In this paper, we expect a well-written abstract summarizing the results. So they have trouble with telling the punchline in the abstract, but that's what we want. Then, a description of the purpose of the experiment, the description of how the sample were selected, how the data were collected including operational definitions, a presentation of the data, including neatly titled and labeled figures and tables, an explanation of the statistical methods used, and a discussion of results and conclusions. Finally, ideas for further experimentation. This is all given in that much detail plus more in the appendix. And so when the student sees what is required, we hope that they include it. Admittedly, even good students don't have a lot of experience with such an assignment, and I allow for a rewrite. So they take all my comments, rewrite it, and we average the 2 grades. It's a big time consumer grading these papers, but we feel that they get a lot out of it. Okay, through the years, problems have arisen with this course, and these are our put out the fires approaches. In a lecture format, when a student walks in late, it's kind of no big deal. Apart from it irritating the professor, you just continue talking on, and it doesn't disrupt the course too much, especially when they slip in the back. But in an experiment format, if they come in late, it's bad. You might be already outside guessing distances. Or you might be already, because we do go out of the room for several of the experiments. And so we had to have some mechanism for discouraging late arrivals. And a team that we put together several years ago, National Science Foundation, when they funded these things, they required an advisory panel that came in and you told them what you were doing, and they gave you all their good insights. And we were lucky to get Bob Hogue on ours and a local chemist. And what they do in a chemistry lab is give a short quiz at the beginning of each lab. And this quiz ensures that students have read their lab experiment for that week, or at least read the boldface from it. because they can pretty much pass the quiz if they read it. And it also is real useful for starting the class on time. It's only a 5-point quiz, but every point counts for quizzes, for students, we know. And so like, here's some of my example quizzes. For the heartbeat lab, describe the 2 methods that we will use to obtain minute heartbeat counts. So if they have a heartbeat and they've read the lab, they probably know that we're going to count it for 15 seconds, and then we're going to try again counting it for 30 seconds. Variability between and within, the second question has to do with that. And these are typical 5-point quizzes. Let's see. I better not use my left hand. I'm just sitting down. Let's see, there's the airplane experiment. 2 uncontrollable factors. Oh, the wind and the rain. Those are the favorite answers there. We get other ones though. What's the measurement of interest? Why do we randomize? And then some questions about the hickory nut. So these are, this is our fix for late arrivals. And it really does fix the problem. Grading policies. We thought the lab approach was a good one, and we thought the students would enjoy it, but we didn't indicate just how much of our final grade it would count. So it's going to count for like a third of your grade or a fourth of your grade. Well, they were upset by this, and they wanted to know exact point values. And so now, a lot of these problems arose in the TA sections because they were less experienced than the teachers, than the professors. And so we actually provide our TAs with what they should use for a point breakdown of these 600 possible points in Stat 201. The long report that they have a chance to rewrite and improve is a whole test grade, 100 points. There are only 2 tests during the semester. Those are the traditional in-class tests where they use their calculator. All the quizzes and the short answer writing assignments add up to be almost a test, 75 points. And then the little quizzes that get the students to class on time serve as the other 25 points. If you start thinking about that, that's, let's see, there is an exam, 1, 2, 3. About a third of the possible points attributable to the lab. And so if the student participates well and comes to the lab, it can really help his maybe dismal in-class test grades. Let's see if I have it down here. There we go. 2 in-class exams, homework. I just took it homework. Lab and the SAWAs, as we call it, another test. Long report, 100. This was one I only gave 1. And the final exam. So that's the breakdown of points. But that quieted the complaints that we were getting about how the lab counts towards their final grade. Because these aren't 2 different grades that are assigned. The way to make this work at University of South Carolina is to make it part of the 3-hour Stat 201 course. We tried the 1-hour additional lab, but nobody would enroll in it. It was a disaster. One of the major problems that we still have is in grading these long reports. I'm not good at it. I tend to, like, one time I'll sit down, and for some reason that hour of grading those 4 reports, a good abstract was real important to me. And then the next hour I'll sit down and, I've got a beef about graphs that aren't well labeled. And so I was being inconsistent in grading these long reports. So we produce what we call the scoring rubric, and it also helps the TAs, the less experienced teachers, that gives a point value to each part of the report. And so they learn that if they forgot to add ideas for further experimentation, because that's pretty easy, you just make up some, that they lose 5 points from their 100 points. Or they learn that an abstract is important to us, worth 20 points of the 100 points. And the rubric has helped. But we would still admit that this is probably an area for improvement, how to get more consistency in these grading lab reports. Okay, I've mentioned Dr. Spurrier, my colleague. He's a detail man. And sometimes this really gets on my nerves, but other times it comes in handy. And he has produced, it's really him, what we call a checklist for every lab. And it's really useful. If you're running short on time and you haven't prepared as much as you should, just grab the checklist for that lab and go through what needs to be done before, after, during, all that stuff, and you'll appear that you really have your act in order. Here's a typical detail of the teacher's manual, because it really is a detail. This is the teacher's manual for the airplane experiment, and they're just 2 pages. And so this teacher's manual reminds the teacher what kind of experiment we're doing that week and what we hope to get accomplished in terms of the statistical issues. The materials needed, this tells you they're set out for each of the 6 teams, these things. It just has so much detail. It's really, really useful. Even tells you what to do if it's raining out, or reminds you what to do. And then if you think that's a lot of detail, here's the checklist. Read some of these things. In advance of lab day, read the session. Work through the session if you haven't already did so. We want our teachers, this is mainly for TAs, to have done it once before they teach it. We have weekly quality circle meetings, and most of the time we've done it together. We want the teachers to go in there and already have team assignments. It just looks better than going, okay, you 4 be on that team and you 4 be on that team. Make sure you have it posted on the board. It just takes a minute, and it appears more professional. Teams have been pre-assigned. It's done randomly, however. Prepare a quiz. Then, before students arrive, post a team assignment sheet. Here's an interesting aspect. I haven't mentioned the videos before. Some of our TAs were basically coming into the lab. It's a new format for them. These are students who were taught, like us, using the lecture approach. That's what they have seen their whole life. Maybe that's changing some. And so they weren't excelling at this hands-on method of teaching. And so they'd come in, they'd go, okay, do the labs, there's your group, do the labs, today's airplane. They weren't motivating the problem. So the 3 teachers made videos, and it's basically a TV program, a 3-minute video clip of our bugs telling the class what we're going to do that week. And they're kind of corny, and they're very dry, not real entertaining, but the videos serve a purpose, and an important one. They set the stage. Anyway, that's the videos. So this checklist reminds the teacher they have to roll the video card and play the video. And then the lab itself. Remember, this is the airplane lab. Encourage teams to be creative in selecting factors. I go so far as I don't want to select paperclip factors, because I've seen every different way paper clips can be added to a plane, and it's just not that interesting of a factor. So I can say I will check with them to see what their factors are and make sure they're interesting ones. There's something written on a balsa wood airplane that says, for longer distances, slide wings, and it either says forward or backward, but it tells you on the plane. And so when students choose wing position, forward or backward, as their factor, I sometimes won't lie, because it tells you on the plane. But then if they come back and go, oh, but we're going to have a second factor and there might be interaction, then I will let them, because that does happen. All these things, again, if you just check through them and do them, it's amazing how useful this checklist is. I sort of laughed at it when I saw the checklist, but now I'm a big convert to the checklist. And so after lab, because probably after that 2-hour period, another teacher is coming into the room to teach it, these things, simple things are so easy to forget, like rewinding the videotape to get it ready for the next teacher, checking paper in the printers. And every one of our 17 labs has this in the teacher's manual checklist, and I just can't rave enough about it. Anyhow, that helped a lot with improving the effectiveness of the labs as taught by the TAs. It helped me too, so I shouldn't say just TAs. The students are required to buy a teacher's manual, a lab manual. And I believe this is the second publisher, because our first publisher dumped us, that this probably is headed for the internet. I'd be willing to put labs on the internet. I have to get my co-authors to agree. Because what happens is professors adopt only 2 or 3 of them. And I don't care, that's fine with me. And so they don't want to buy the whole book, and so book sales are not thriving. We made a sort of an ethical decision to donate all the royalties from the sales of our book at our university, you know, like when we make our students buy it, back to the university. So right now, when I get my royalty check, I pretty much sign it over to the University of South Carolina. The only thing this book earns me is a very nice handwritten thank you letter from President John M. Palms, president of my university. That doesn't bother me. I'm not into selling a whole bunch of books. This has been mentioned before. We don't have any gone are almost all hand calculations. If you think about this, we've lost a whole hour-long lecture because the third time they meet each week is at the lab. And so you have to delete some of the curriculum. No more calculations of regression lines by hand. Fine with me. And we used to do a multi-column display, xi minus x bar, yi minus y bar, blah, 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 to show them how to calculate R. And I'm more than happy that that's out of the curriculum. Surprisingly, our TAs have more trouble eliminating hand calculations than the professors. I don't know why this is, but when as the director of this big 300-person class, I'm required to read through their exams before they give them. And I continually find sort of silly problems like, well, I call them hand calculation problems that we've preached at I'm not to include any longer. So they have more of a problem eliminating it from the curriculum than I do. I don't have any problem with leaving out hand calculations. I still do X bar and S, but that's hardly a hand calculation because if they learn their calculators, that's really entering data calculation. Did you have a question? Okay. Anyhow, that's, you've seen this before. When we want to learn how we're doing, just a sort of checkpoint and see how the students like that week, we hand this out. And it's the lab version of the 1-minute paper. You can do this in lecture too. You know, you ask them what the most important topic was. And while you think you might have given an excellent lecture on topic A, nobody answers that answer. It's a very eye-opening experience for some of us. What point was unclear? What would you like to learn more about? And for the lab version, we asked them how this lab could have been better. Taste test somebody wrote recently, this lab could have been better if Cindy Crawford would have been serving us Domino's pizza versus Papa John's pizza. You get silly answers here. And one of the major pluses of the lab approach, in addition to the students really having fun, is they learn important concepts like the importance of randomization. In about 10 of the 17 experiments, a coin is used to implement randomization. It just comes up over and over and over again in the experiments. Interaction, the 2x2 factorial experiment, the aspirin dissolving experiment, and the airplane lab experiment shows interaction. Nonlinear relationships, the lab I'll talk about tomorrow in detail, the distance guessing lab shows them, often has the students exhibiting a nonlinear relationship between their guesses and the true distance. No surprise, we can guess shorter distance more accurately than longer distances. Calibration, design of experiments, and more. Students overwhelmingly like this approach. We find that they'll still skip lecture but come to lab. And we see comments like they like Minitab in the end, and words like fun, and I learned a lot. And so, you know, we're proud of how it's working. And that's all. You're supposed to know that was the end. At this point, I'll answer any questions. I'm almost out of time.
Do you go through that whole book just the essentials? Or what chapter?
Yeah, we do. We do.
And when when they do their lab reports, does everybody write a lab report, or is there one report per group?
Everybody writes one. Yeah, they might share the same data because if they've worked in groups of 4, then 4 of them have the same data, but they all write their own report. So you end up grading 46 reports if you have a regular section class.
Is there a problem with the students getting to know from their friends what the report should look like?
Yeah,
Or
all the fraternities and sororities have the SAWAs on file. That's a short answer writing assignments. But the thing is, every person has a different data set, so you really can't copy it because the SAWAs are so wedded to your data set that if you copied the one that you found in your fraternity file cabinet, it wouldn't make any sense at all because you're reporting X bars and S's and shapes of histograms. So they can't cheat as easy as they could in a different format.
They could look ahead and say, well, this is what we should do without the rule. Maybe histogram is skewed the other way, but not.
That's right. They can look ahead, but if they're going to take the time to do that, so be it. Yeah, we don't. I'm sure that there's some cheating that goes on along those lines.
Is there any problem with keeping the lecture and the labs in sync? Or that is it?
Well, we have certain topics that are covered in the lectures that are well documented. Like I know when I go into lecture number 13 that I'm supposed to get through these 2 sections in Bob Johnson's book. And if I don't, then the lab they do that Friday will be, they wouldn't have seen any lecture on it. So it's very important to stay on the schedule. And the schedule has some catch-up time in it and so forth.
How do you get your colleagues to go along with that?
Well, there's only one colleague that teaches. It's all the TAs that are underlings. They do it because they have to.
Hand out your handouts.
Yeah, I've got handouts. And I think my colleagues would, because again, we're a pretty good bunch. We don't fight a lot. And I mean, it's not fun to go in there and do an experiment with the students having learned a t-test, so it would behoove you to stay on schedule. Any other questions? Uh-huh.
Is this a 16-week one?
42 50-minute, 42 lectures, but 12 of those are labs. So how many weeks is it? I think it's 14 weeks. It's a semester. 42 class meetings for Monday, Wednesday, Friday. Yeah. It's chock full, but we can get through it. Okay, well let's end. Roxy's next, so I need to get off the computer.
And we're going to talk about one in particular today called, write this down, real and perceived distances. And we're not going to actually do the experiment. We're going to have the data that was collected from students that did the experiment. But we'll work through it in the same kind of way. Okay, thank you for coming.
We're going to use the data set that Bob Johnson put on your black disk. So you guys stick that in the form. If you don't have it, it's probably Okay, I'm going to have a little bit of presentation before we start. I want to give a short description of all the lab experiments before we zero in on one particular experiment, distance guessing lab. The format of the lab is an actual separate class meeting from the usual lecture meetings. Our students come to a different room than the lecture room and carry out experiments in which they generate their own data. It's not data that we give to them. And then use Minitab to analyze the data. We find a big plus to the idea of the student having their own data. They get a lot more excited and inquisitive about the experiment, I think. The lab is set up to be self-paced in the sense that students work through these chapters in the lab manual. So we don't, as the lab teacher, we don't do like flit around and facilitate, maybe try to get them to think about their data. But because the lab book has a lot of detail about how you do the Minitab and so forth, the students, if they have a couple brain cells in their brain, can do it pretty easily using just the book. We do familiarize them with Minitab and the computer on week 1. We carry out some low-level experiments during the first week, because if you think about it, during the lecture component, you're not doing that many high-level things at the beginning of an intro stat class. For example, the heart rate lab only illustrates summary statistics, both descriptive and numerical and graphical on students' heart rates. Author is kind of a neat one, in which the author of a disputed manuscript is discovered through the use of descriptive statistics. We grow plants for some of our smaller sections and measure their heights on a weekly basis, providing us with a nice longitudinal data set that lends itself to log analyses later on in the semester. In week 5, we go outside, the whole class, 24 of them, trumped outside, and some distances that have been predetermined are guessed. We use that data set to illustrate scatter plots, linear relationships, nonlinear relationships, regression, of course, and even calibration. This is a time series lab. Students count cars coming through an intersection in 15-second intervals. It's a neat data set that often shows pronounced cycles and sometimes trend. A question of taste is our taste test lab. And in that one, the students carry out, generically we call it a taste test, but they compare several different products, one often being a name brand product that, say, costs more than a generic brand product. And by asking the classmates to choose their favorite one, we carry out a binomial taste test, that illustrates the binomial distribution. For example, this is overwhelmingly the case. We find out that the cheap cola, like in our area of the country, the cheap cola's Vino brand, is preferred over the more expensive name brand Coca-Cola. We provide students with 2 cups, and they, using randomization, they test one, and then drink the second one, and the taste test givers know which is which, and mark down which one they prefer. We compare foods like Planters brand peanuts to cheaper peanuts. There's a big dollar difference. Cheaper off-brand peanuts. That's another product which doesn't pay to buy the name brand peanuts. Recently, they've requested some comparisons of all these fat-free alternatives, and those aren't very well liked. And finally, we don't always compare foods. They do things with touch, and it pays to buy nice toiletries. They can leave the room for them. They actually smelled it, liked it, the good stuff. This is one in which carpet tacks are measured using a micrometer. Now we're getting into the rest of the semester where they're now using some inferential techniques. For example, the airplane experiment, in which a balsa wood airplane is flown under different flight conditions, illustrates a 2 by 2 factorial experiment. Rating strength, in which strength of facial tissues is measured by placing fishing weights on top of the tissue spread over an embroidery loop, illustrates a 1-sample t-test. These, near the end, we're into paired t-tests and independent samples t-test. And then the last one is a favorite, illustrates multiple regression. By measuring several physical attributes of a hickory nut, the students build a multiple regression model that surprisingly and accurately predicts well the weight of the hickory nuts. They measure 24 nuts. Okay, so now we're so I'm going to talk in detail about the distance guessing lab. It's one of my favorites. Students come to the lab, and as I mentioned yesterday, to get everything started on time to give a quiz. So they take their quiz because they would have pre-read Section 5 of the lab manual, and then we're ready to go. They go outside, and we stand at the same physical spot. We call it the base. and they guess the distances, as we call them out, to 13 landmarks. My campus is an urban campus, as it's called, because it's right in the heart of the city. But the campus planners, I think, have done a good job of maintaining and keeping green space. We go to a part of the campus that is called the Horseshoe, and there's lots of trees, and there's no cars, and it's real pretty. Students like that aspect of going outside. This is the Horseshoe in rain. But we stand like right here, and the students stand this way, like a couple football fields in either direction. And we tell them to guess to the distances in feet to 13 predetermined landmarks. And we have predetermined where they're guessing, because it's kind of important to have a nice collection of distances. Some of which are short distances, some medium distances, and then we have them guess distances that are up to 300 feet away. They're not as good at guessing those distances, but still the experiment works. Oh, we see things like they're often embarrassed to guess. They're writing down their guesses, nobody else is looking at them. They're going to analyze their own data, but they're often embarrassed, and you have to get them over that. It's amazing what students get embarrassed about. But after the data are collected, everybody has 13 guesses. I keep mentioning 12 and 13. The data sets that you'll analyze today are only 12 points big. 12 guessed distances, and in another column, the true distances. But there is a 13th distance, and we call this the mystery landmark. That 13th guess enters the picture at the very end, in which their guess is calibrated to become hopefully more accurate. For example, if a student is a bad guesser, they consistently under-guess by half, like the true distance is really 300 feet, but they guess 100 feet, 150 feet, then it's pretty obvious what you do. To their guess to calibrate it, you simply double it. It's a little bit more complicated than this, but not much. We use a reference line, a regression line to calibrate. And so here we go. The only material needed for this lab is a tape measure. And I haven't mentioned how we get the true distances. As an instructor, I know the true distances. We use the same 12 landmarks every time. But we want to also introduce students to the idea of measurement errors and measurements. So after the distances are guessed, the students working in teams of 3 or 4 measure the landmarks. Not all 12 of them. You assign each team, I think, 6 landmarks. So every landmark gets measured 3 times. It takes about 15 extra minutes. But it's real valuable because when you come inside and spend another 15 minutes working out the true distances, each of the 3 teams that measured each landmark will call out their distance. And for a short landmark, the teams almost will often agree to the nearest, a couple inches. Like a short landmark is 4 feet. And the 3 teams call their measurements, and it'll be like 4 feet, 1 inch, 4 feet, 2 inches, and 4 feet. And we take the median of those 3 measurements. On the other hand, long measurement, like a football field measurement, the 3 teams don't agree. And sometimes the disagreement is in multiples of 50 feet, because that's how long the tape measure is. You can see what's happened as they're counting how many times they've used the tape measure, they lose count. And so it's not uncommon to get measurements like 200 feet, and then the other 2 teams closer to 250 feet. And everybody laughs, and you have a good example of how the median is better than the mean as a measure. So at that point, we're about an hour into the 2-hour lab period, and then the students begin working on their own. Everybody has their own data set. Some problems that arise, I want to point these out before we get to the data analysis. Students are real hard on tape measures. We go through a lot. And as much as you tell them, they're going to break them. It's unbelievable. And they get them wet, dirty, then they'll start winding them up. They can hear that grit just going away, and they keep winding, so we break them off. We have a checklist that helps the instructor, because it's not always me or another professor. These labs are taught by TAs. And this checklist, I want to show you a little bit about the detail, helps the teaching assistants remember to do everything that there is to do. It's kind of a lot to remember. So they have every little thing. Remember, someone was laughing at me. The checklist has them remembering to plug in something because the video is played at the beginning of each lab to set the stage. But these checklists, I'm not going to say too much about. And they remind me, I use them to have your act together, have everything done. So if anything, the challenge of these labs is to get them organized and for them to go smoothly, because there's just a lot to remember, especially one that has a lot of materials, not this one. I think at this stage I'll hand out the handout, Jan, because we're about to open up the data set. And again, the checklist. When you open up the data that are already entered, remember that the students themselves enter their own data. So you're working with some example data from students who took this lab this summer. And the names have been changed to protect the kids. Let's see. Here's how much detail we have as an instructor for the landmarks. Because again, it's important to have landmarks that represent a wide range of distances. And so when we go outside, I have this sheet with me. Students don't have this. And we say, okay, this is your first landmark, folks. You're going to guess from the reference point, which is this lamppost, to that brick right there. And if it's not too far, I should run over there. We start off with an easy one. This first landmark is only about 4 feet long, I think. And then, you go to the second one, you make sure they're writing down their guesses to the nearest feet. Some people don't want to round off, so they'll guess things like 157 feet and 3 inches. Kills me. But 12 guesses, and this is one of our locations. A typical lab has 24 students, and sometimes labs meet at the same time, and there's 2 groups. So we have another set of landmarks. So the second group won't be all at the same location. And we also remind ourselves, and the students don't know this, of how far the mystery landmark is. This is the very last landmark that is guessed. It's not part of the Minitab data set. Minitab, if you have a point in your data set that doesn't have both an X and a Y coordinate, you can't graph it. But this is the landmark guess that they'll eventually use the regression line to adjust, or as we call calibrate. Okay, what I've done is from this summer's lab, saved a data set with several different students. We might have just enough so everybody can be a different person. I want you to open up Minitab now on your computer. At home, I go fire up Minitab. Icon on the desktop is not there. Where it is, Jan will tell us.
We start, go to programs, departmental applications, mathematics. Down at the bottom is Minitab 12 for Windows. And then we click on Minitab 12.
It's important to have Minitab open before you try to open up the data set. The data set wasn't saved in the MTW data set, so you won't know how to open it. So when you have Minitab open, under the open worksheet, under the file command, on your floppy, the A, open up the file called distances, Lory Tunes. It's pretty self-explanatory. That's how Bob saved it. It's under A.
The A click on the arrow and look in to open up A.
To the floppy, put that on. One down. There. It's called distances dot Lory Tunes. Okay. And here's the problem.
Yeah.
This is because when you want to open up that, because it doesn't have the, you first want to open up that notebook, because that's where everything is. It takes some time to do it. It was a little confusing when I did it.
Okay. I see. And then we want to do
Yeah, you make sure it allows you to look at all files because it doesn't have the right extension. And I know it has the word distance in it, and I think it has the word Laurie Toombs in it. Did you get it open? Go ahead, open it up. It has the word distances in it, and it has my name also. Here's what it looks like. It's real small.
Yeah, so that's, all the way down here, over here, I've done,
We use Minitab exclusively for data analysis. It works real well. And by this week, students are already pretty good at it. Okay, let me make the data big. Here we go. So if you see what the data are, I've entered into a data set a bunch of people's guesses. We have Ray, Howard, Jennifer, Jim, Lee, Seth Garman, Kelly, Geary. And I know how each of these people did, but you're gonna be able to discover that on your own. I've also entered the true distances, and these are the medians of the 3 measurements made by this particular class. They're taken as the true distances. The first stage in the analysis is a simple scatter plot. And the only thing really that's left to be determined is what do you put on the y-axis and what do you put on the x-axis. And so what we're going to do is on the y-axis put our guesses, and on the x-axis put the true distances. Okay, so how do you do a scatter plot in Minitab? And that's where in real life the students go to their book and they look at the page. But here's how you do it if you don't already know. How do I get this minimized? So what I want to do is get Minitab back. Or I'll go through this. Control, or control, alt. Really? I know it'll work this way too. Okay, pick one of the columns. I'm not going to have you, I'm not going to assign people, but be somebody. We'll talk eventually about all 6 or 7 people. Lead. It's like, if you want to be Lee today, be Lee. If you want to be Jim, be Jim. But, you know, obviously you can only graph one person at a time. So what we're going to do is use Minitab to get a graph. I'm going to just go with, I'll do Gary's, since you did guess. I'll do Gary's guesses versus the true guesses. And one of the neat things that we do on this very first scatter plot is append the scatter plot with the y equals x line. Because the 45-degree line, perfect guess, the y equals x line represents perfect guessing. So here's what you do. Plot is a graph technique, so you go under graph, plot, and open up that dialog box. I like Minitab. Pretty self-explanatory. The y, as I told you, is going to be our guesses. So that's who depending on who you are, we'll put Lee's guess. I said Gary. We'll put Gary's guesses on the horizontal axis, and then for every guess, there's a true distance, and the true distances are the x variable. Okay, before you click OK, there are some ways that we annotate this plot, because we want the students to print them out eventually. So we do tell them to put a title. You know, my guesses, or often Gary's good guesses. Because Gary is an excellent guesser. I accused him of fudging his data. It's so good. But everybody else is not as good. And it's okay to be not a good guesser. And then before you click OK, do the following. Under annotation, kind of near the bottom, there's a line option. What we're going to do is annotate our scatter plot with a line. As I said, the line of perfect guessing, or the x equal y line, has meaning here. And we provide the students with pictures of these screens. It's a little bit confusing, but to add a line to the scatter plot, you have to tell Minitab what are going to be the x coordinates of those points that will be connected with the line, and what are going to be the y coordinates of those points that will be connected with the line. And so what we want to do to add a line is just type the same variable in twice. A variable called C9 is the true distances. That's the one I use. But if you tell it to plot C9 versus C9 connected with a line. Yeah, I think true though you have to have little quotes around it. True, actually you can do Gary, you know, work. The key thing is the x variable has to be equal to the y variable. And interestingly, the x has to come first. So this tells us that here's the x points, and here's the y heights. Plot those points, but because we're using the line option, connect them with the line. Click OK twice. OK to get out of this submenu, and OK to plot. And you'll see how good a guesser, at least in this case, Gary was. Yeah, because if you look at it, here's a distance of 272 feet. He guessed 275, which is amazing. And we'll look at other data sets in which this is the case. Most people, here's what I do, even if I've been doing this for 10 years, I can guess a little 3 feet distance is pretty good. But then once you get, past 30 or 40 feet, my guesses become less accurate and I underguess. So my guesses are less than the true. And so my data set typically is a pretty nice linearly related cloud of data points that falls below the 45-degree line. Okay. And that's more typical. Let's do Lee next. Do the same thing with Lee's data. He's a good illustration of overguessing. Yeah. Lee, what you do, close this box or minimize it, whatever. You do the same song and dance, that is plot. This time we'll enter Lee as the y variable. And I really do like the first plot having y equals x line. And so keep that in there. And I think it should just say what we just did for line, so it's already set up to go. And click OK, twice. I should probably change the title. Now I have Lee. And here's Lee's guess. It's more typical. Well, this is one of the. It was C9 and C9. The main requirement is that we want the points to be the same two variables, so we get the y equals x line. Do any two variables that have data. I just always use C9, C9. Okay, look how Lee guessed. When the distances got further, he tended to overguess. But remember, the goal of this experiment is to illustrate linear regression or actually nonlinear regression and calibration. What we're going to do after we look at a few more scatter plots is fit a line to these data and then take Lee's guess for the mystery landmark and calibrate that. And that's not exactly what we call predicting, because remember the guesses are along the y-axis. So preview of coming attractions, what we'll do, we'll fit a line to Lee's data. We'll see that, oh, he guessed 100 for the mystery landmark, and that gets calibrated down to 80 or something like that. I haven't given you the guesses. I've got everybody's guesses, but they're not part of the data set. Okay. Do one more. B, for example, Ray is a good guesser. Howard is a good guesser. Here's a more typical. Jim is an overguesser, just like Lee. Let's see. Do Kelly. Kelly is a girl, and she's more like what I do every time. If you look at Kelly's graph, she's not a perfect guesser like Gary, but when she's wrong, she's consistent wrong. She's consistently wrong in that she underguesses. That's like a real good data set. We're going to see when we calibrate it. When we use it for calibrations, it just works like magic. Some things, depending on the level of your class, you can illustrate at this point. It's not uncommon to have this problem of variability increasing as x increases, because as they guess further distances, it's harder to get them accurate. So if you drew you see sort of the cone-shaped scatter plots that are indicative of the problem with increased variance. But that's about the scope of this class, so I rarely get into that. What I hope to get out of this is students understand their data, just what they're plotting. They print this graph and answer questions like, are you an underguesser, or are you positively biased? And then the second stage, of course, involves fitting a line. Okay, so I've illustrated Gary's good guesses, Kelly's under guesses, and Lee's over guesses. Let's go now to the next stage in the analysis. We just did all this. Obtain a scatter plot of your data. If you were a perfect guesser, what would your scatter plot look like? And obtain a scatter plot of line perfect guesses would be. And that, of course, is to do the plots. This is to make them think about how their guesses are. It's almost always the case that if they're not a good guesser, they're bad in a consistent way. Like Kelly, the underguesser, or Lee, the person who guessed too far. So they learn terminology like negatively biased, positively biased, that would be Lee, over guesses, and good guessing in Gary. Okay, so here comes the fitting the line. You can sort of develop your own level here because some of my classes understand nonlinear regression and they can fit more than a line using Minitab. But let's just stick to lines here. Okay, under the Minitab stat command, there's something called fitted line plot. Stat line, stat command, regression. And again, in the textbook, this is actually printed out. We capture screen, edited out all the background stuff, and we tell them, you know, here's where you're going to go. Fitted line plot. So let's look at the dialog box for the Minitab command, fitted line plot. Response Y. Well, by now students understand that Y variable was plotted on the vertical axis. It's always the guesses, their guesses, and predictor true. We fit a line, and you know it's pretty self-explanatory. Let's plug in. We'll do Kelly first. So what we're going to see is Kelly's data set. It's a graph with a line, the least squares regression line, flowing through the scatter plot. Bear with me. I'm going to come back and do Kelly again to see why. I actually like them to save their fits and do a final plot that has everything on it. Remember, this isn't the y equals x line anymore. It's not on here. In fact, it's like down here. Okay, so that's Kelly's regression line. There's slope, intercept, a nice R squared, 94%. And for your information, Kelly's guess on the mystery landmark was 65. 65. The distance of the mystery landmark is 104 feet. So if we find 65, they can do this using the ruler method, or they can actually plug it in as the y coordinate in the line. It's about right here. Reflect over to the regression line. Look how well it gets calibrated. Just using the eyeball technique, 65 becomes something close to 100. 65, down to the over to the regression line, corresponds to a true distance. I think it comes out to be 97 when you actually plug it into the y part of the regression equation. So her guess, calibrated, becomes 97, and she's real delighted when you tell her that the true guess is 100. I mean, the true distance for that mystery landmark, the one we did not measure, is 103 feet. Calibration doesn't always work. Kelly is an example where it works pretty well. On Gary's graph, even the one that guesses so well, his guess doesn't change at all because his regression line is nearly the y equals x line. I'm going to stick with Kelly and do one more thing. If you go back to the Minitab command under stat, fitted line plot, there's an option where you can tell it to save the fits. And this is real common, you know, in SAS and all the other things. And under storage, click to tell it that you want to save the fitted y values. what will happen is it'll do the same thing it just did. Default, it will print out a nice plot of the data annotated with the regression line. But in this next available column, I believe it was C10, will be Kelly's y-hat values. Why do I want to do that? Again, we'll still see the same plot. So here comes the same plot. But why did I do all this? Look at the data now. It's been appended with a new column that are the fits for the regression equation for Kelly. So now I'm going to be real fancy. I'm going to go back to scatter plot. I'm going to have it scatter plot the data that is Kelly versus true, and I'm going to add 2 lines to the scatter plot. One of the lines will still be the C9 line, or the line of perfect guesses. The other line will be these fitted y values, the regression line. And it's a nice sort of end-all plot because it shows everything, namely that she's an underguesser, but that she's consistently an underguesser. So Kelly versus true, we're still going to have her 12 guesses on this graph. Under the annotate, add a line to my plot command, I'm going to fill in 2 rows. 2 rows. So I want 2 lines on this plot. Now this kind of was tricky at first. We're so used to thinking y comes first, followed by x. We need to add first. Right here you have to give it the x variable first. The x variable followed by the y variable. So here's how it works. True, C9, followed by the fits, C10. And that will succeed in adding a second line to the plot. That is the regression line. Remember, Kelly's an underguesser, so now that clip reminds us again that she is, because there's the line of perfect guesses. This is her regression line, obtained by saving the fits and annotating the scatter plot with the second line. And so I have to print this final graph out. And at this point, because we, as in many intro stat classes, we did regression like in week 4. So they don't get a lot into inferential regression. I guess they can plug it into line. But we have them calibrate by taking a red pen and a ruler and finding along the vertical axis their guess. Remember for Kelly it was 65 feet. And then reflecting, not using the y equals x line, because we're not perfect guessing, but using their regression line down to see what the true distance that corresponds to. And so the last question on the short answer writing assignment for this distance lab, where is it here? Is about the calibration part of the experiment. What was your initial guess for the mystery landmark? Well, if we were playing Kelly, 65 feet. Now adjust your guess by using your fitted model. The graph is drawn on. My guess gets adjusted to 97 feet. I think that's exactly what happens to Kelly. And is that a better guess? Because at this point they know the true distance. Yeah, 97 is a lot closer to 104 feet than my initial guess. The second person that we looked at was Lee. Remember, he was the overguesser. Here's how his graph looks. He guessed 160 feet for the mystery landmark. The true distance, the same mystery landmark as Kelly's, is 104 feet. But look how Lee's graph looks. This graph does not have the y equals x line on it. That line kind of goes like this. And here's Lee's regression line. There's his initial guess, down to the adjusted guess of 109. So another example where calibration works, and it works probably 90% of the time. Some people have crazy data and calibrated their guess is many closer to the true guess than it was to begin with. So I've admittedly picked 2 excellent examples to illustrate this experiment. Okay, at this point I'm pretty much done, but I consistently get comments from people that say, well, I can't have my students meet 2 hours because it's only a 3-hour class. And you still can do some of these lab experiments with the students analyzing their data on their own outside of class. That would work. It's probably not as effective though, because as I flit around the room and lean over and say, tell me about your graph, that really makes them think, and I think that serves some purpose, being in the lab. And then the other approach is something we've seen some very good talks on, is to have students working with real data, but real data that has been provided to them. It does take time to generate your own data. Our experiments are really low level, and they're not even high-tech experiments, because they have to be because of time and money constraints. But I cannot underestimate or the value of a student owning his own data is big. You get a lot more excited about it than if we handed them data. We did one experiment in which we measured the absorbency of paper towels. So we actually have them take a paper towel and fold it once this way, make it smaller, and fold it like this. So they're working with little squares and tongs. Dip it in water, have it suspended for 20 seconds, and then measure how much water it absorbed. And the name brand feels better, it's thicker, absorbs a lot more water than the generic brand. It's a real clear-cut statistical, very statistically significant difference. But the students will notice, as they're doing this experiment, they do 20 of each, that the name brand is a little bit bigger. Not much bigger, but the square of the paper towel is a little bit bigger. And so on their own, it's very, very common that they'll say, well, that's unfair. It has more surface area. And they'll standardize it by dividing it by its area. They'll take that absorbency measurement for each paper towel and divide it by the total number of square inches to make it more comparable. And they'll still see that, say, the name brand wins over the generic brand. And I conjecture that that kind of inquisitive stuff wouldn't happen if we just gave them 2 columns of numbers that were already the measured water absorbencies. That's all the formal stuff I have. We only looked at a couple of columns. If you want to look at any other person's guesses, I'd be glad to help you. Are there any questions? Yes?
Students work together in groups.
For this one, it's an independent person one. The only group part of this experiment is when they do have to measure their 6 assigned landmarks, we allow them to work in groups. But every student has his own data set for this one. Other ones, yeah, they work in groups of 4.
Do you have mixed groups?
No, we assign them. That's a big area of research, but I randomly assign them randomly. And so every week, if it's a group experiment, I post a list of the groups on the board. You notice the checklist had post-group assignments. And so they know that if they're in group 2, that they should go sit at the table that has group 2 written on it. We have 6 tables in the room. Stuff like that.
And so you're not consciously composing the groups to have a high grade student and a middle grade student and a low grade student,
No.
or any of that?
There are very big components of other approaches. I have one friend who goes so far as to give her class some sort of questionnaire at the beginning that puts them in a personality group, and she makes sure that every group has a type A and type B in it, or something like that. I'm too lazy probably, and also studies have shown that maybe that's not always worth it, all that effort in the end.
And so they'll wind up working with lots of different students.
Pretty much everybody works with. And it's also kind of an interesting study of randomness because I promise I do it randomly. And there was one obnoxious character in the class, redhead. I don't know why it's relevant. And this poor woman got paired with Jeremy the first 3 weeks. And she came up to me and she said, I don't think I believe you're doing it randomly. You're putting Jeremy the 4th week in a row. And it really was random, but she just wasn't lucky that semester. And we have some pushy people who don't allow other group members to participate. So these are have to rein them in. We've actually gone so far as to record a video, Dr. John Spurrier's mug, talking about working in teams, the politeness, the importance of politeness and not being a pushy do-it-all and respecting your team members, regardless of race, creed, or color. Because we had some of that going on where they were too kind It's evident that a lot of these freshmen have not ever worked in teams in high school. Some of them are real bad team workers. Any other questions? Okay, that's it. Make sure you get a handout. Don't forget your diskette. Plop it out of drive A, or that sign in earlier. And I guess close down mini tab to be polite. Close down mini tab by exiting.
I have a question. When you say the bit, what's the extension on that?
It's just another column in the Minitab file called distances. So if you notice what happened is our data set, the lots of data numbers, had a new column in it. Here it is.
I didn't see that, right?
Well, it's on there. So there's no extension on the columns. The extensions are on the files.
I know, but you said that, graph,
Yeah.
you say that graph, you could access it later, how do you access it?
Oh, I didn't save it. Here's what you save.
Ah,
You make that window live,
right,
and
okay.
you do save draft as whatever you want to save it as.
okay.
We actually have a print graph at this point, and not saving it.
Right.
That's a good question. I think allowed to save it as a, like I say, please,
And
as a mini tab graph, or you
okay,
can,
yeah.
yeah, exactly, VFD, VFD. That's how you do it. That's a good question.
And then can they put headers or footers for the titles and give their names on it, or do they have to build their names into their title?
Now, the new version of Minitab allows you to add the graph by just clicking on it. You can change the colors and text. And might teach them this way of making their graph fancy before they print it. Yeah. I'm very happy with Minitab. We're going to continue to use it. I think it's fun and it serves all the purposes that we need.
It's also very easy to use.
I think it's easy. They complain a little. Like, I told the Minitab representative yesterday that it's kind of confusing when we wanted to add this line to the graph, that the two variables I've inputted were C9 and C10, because we're so used to thinking Y comes before X. We just filled out scatter plot screens right and left, where the very first thing you enter is the Y variable followed by the X variable. And all of a sudden, the line option of the annotate plot, you have to give it the X coordinate first. And you do, or else your line would be up like this, and it wouldn't go through the cloud of data points. And so there's little glitches like that you have to be aware of. And, oh, here's another common one that this drives me crazy. The students will often enter the variable name in the first column, the first row, rather than, and all of a sudden that column gets branded an alphanumeric. And it's a little bit of effort to change it back to numeric column. But that's life in the computer world. It's kind of good that they live through these little glitches.
How much does the lab book cost on the edition?
Yeah, we use Johnson and Kubi's. It's the black soft textbook, so that's our textbook, and it gets bound, or used to get bound, like wrapped in plastic with this, and this added about $23 to the cost of the textbook. They were spending about $50, not more. I don't know, on the two books. And they tear things out of this, so it's unlikely that they can sell it back. That's a big deal with our students.
That doesn't equal the standard textbook.
I don't know. You can write down information for it. It just got picked up by this publisher called Whittier Press, because Duxbury dumped us. What we find is a lot of teachers like you all want to use one or two of the experiments, but not all 17. And I can understand that. So you don't buy the whole book. So it's not a bestseller. I'll never buy my new Lexus Sport Coupe 100 from it. And it's probably next generation that it'll exist on the internet. Where you can just download whatever chapter you want. But it's really useful because if students look at it and go through it page by page, they can do these two kind of confusing graphs without me up here talking at them. Because our labs are not equipped with this. We don't have something like that in the labs. And there's equipped with sit-down parts.
And are they doing analysis outside of class, or they're wind up actually being able to do everything during that?
It's a
reserve
2-hour period.
Yeah. So they really never need to do these kind of stuff outside and for do something.
Well, not with these experiments. We give them assignments where they do something similar on their own. But, and that's dependent on who's teaching the class. They can finish everything about this distance guessing experiment in 2 hours. This experiment, for example, has them turning in a one-page assignment that is the answer to those 3 or 4 questions. It's called a short answer writing assignment. It's a page they tear out. And all of them will give that to me before they left. They're all done. Nothing's hanging when they leave that 2-hour lab period.
But they do wind up in the 7 to 10 assignments on their own.
Yeah, I had some more too. Not all teachers do that. Some teachers say they get enough mini tab from this, and the homework outside of that is more calculator-based homework. I'm moving away further from doing hand calculations, so I have other mini tab assignments in addition to these. There's 15 labs. 2 of the labs, they do 11 labs, and 2 of the labs are periods we use for the exam periods. So 2-hour periods.
Can you give me the ISB number?
Yeah, I'll just leave it up here. We'll let you all go now. That's the Whittier ISB. And it's just Dave's number, probably Whittier. It's once you buy it, you might. Maybe we can use the list here. See, I actually have your, here, this is probably more useful. Great. Thank you so much. We're done? Oh, wow. It's cute, but, no, it's not. Sorry. Oh, they didn't want Canada.
Thank you very much for that. I'm introducing to variable statistics for my first test. This coming test, I'm going to get a mini tab project.
Yeah, this is
On this
fun.
time. I can just jump at the lines. You know, that line.
Yeah. There's also a regression.
Yeah, right.
Spits everything on the session window. We do, I guess, right? I'm gonna open this.
Oh, my gosh.
Are you a frosting first or a cake first person?
Oh, pretty. Am I what?
A frosting first or a cake first?
What's that mean?
Oh, it's one of those personalities. You either frosting first or the cake first.
I'm not either of each.
This is pretty. It's heavy.
Yes, it is.
Very exactly.
My new pen should be a usual. Thank you, thank you. I am really excited by these kinds of things.
Well,
Statistics more interesting.
cities, their holdings are different, because their catering is different. It's real unfair there, right? And like one's in the dominantly black place, and I find some groovy stuff, but I never see the white one.
Now there you go.
That's good. You don't have to worry too much with anyone matching up too much. So did you put all these mouse pads around?
That was the handiwork, yes.
That's good. Talk about advertising.
That's exactly, yeah, any way we can. That's right. Well, we took you up on breakfast this morning.
Oh, good.
We dined in-house today, so. Last time was a Bourbon Creek.
Oh, did you go
Yeah,
there?
I had a couple phone calls to make, and so around 8 o'clock we went over, and my meal was great.
Oh, good. Yeah, that's a neat place.
Yeah, I was really happy.
Wow.
Yeah, absolutely.
My daughter Ruby. Oh, nice to meet you.
So he's taking
Yes, I never had Ruby. No. Oh, you want to? Okay.
this is good to go. Take my phone and get it off to that too.
No, it's not that.
Yes, yeah, unfortunately, I was pretty not going to get you our data before